Dr. Sharmishta Lahiri, Associate Professor Physics in Sri Aurobindo College. In today's lecture, I will be talking about the thermal properties of material. Okay. In my last lecture, I had talked about the lattice vibrations, and they are useful in understanding the thermal properties of materials. For these, I will be referring to these books: Introduction to Solid State Physics by Charles Kittel, Solid State Physics by M.A. Wahab, Solid State Physics by R.L. Singhal, Solid State Physics by Ashroff and Mermin. What is specific heat? Specific heat is the amount of heat that must be supplied to a mole of a solid to raise its temperature by 1 degree. Specific heat is defined as the amount of heat that must be supplied to a solid to 1 mole of a solid to raise its temperature by 1 degree. Now, when the heat is supplied to a solid, its temperature and its internal energy increases. The increase in internal energy, it can appear in two forms. One of them is an increase in the vibration of the atom about their mean position, which we define as the lattice specific heat. An increase in vibration of the atoms about their mean position is defined as the lattice specific heat. And the second case is an increase in kinetic energy of the free electrons, which we call as the electronic specific heat. Now, to measure the specific heat, we can either keep the volume constant or the pressure constant. In general, it is the volume which is kept as a constant, and specific heat at a constant volume Cv is defined as dE by dt at a constant volume. E is the internal energy of the system and T is the temperature of the system. There are a few laws which through which we can understand the kinetic energy. We can understand the specific heat of a solid. The first one is the classical model, which is the Dulong-Petett's law. From the kinetic theory of gases, the kinetic energy of an atom of a monoatomic gas at a temperature T is given by 3 by 2 kT. K is the Boltzmann constant. Since an atom has 3 degrees of translational freedom, therefore, the energy will be half kT associated with each degree of freedom. For each degree of freedom, the energy associated will be equal to half kT. Now, to each of the translational degrees of freedom, there will be 2 additional degrees of freedom. That is because energy, it can appear either as a kinetic energy or as a potential energy. So, if there are capital N number of atoms in a solid, which is equal to Avogadro's number Na in 1 mole of the solid, then the total internal energy can be given will be given by 3 into 2 into N into half kT, which is equal to 3 NKT, which I can write it as RT, 3 RT. So, the total internal energy will be equal to 3 RT, where K into N is equal to R, and which is the universal gas constant. This means the specific heat at constant volume, which is given by dE by dt at a constant volume, that will be equal to 3 R, which is 5.96 calories per mole per Kelvin. This is the Dulong-Petett's law. This shows that specific heat is independent of temperature. According to Dulong-Petett's law, that is the classical theory, specific heat is independent of temperature and it will remain a constant for all temperatures, and it will have a constant value of 3 R. This is generally found to be correct at room temperature and above for elements which have a weight greater than 40. Where it fails is at low temperature, the specific heat at high temperature, it is okay. At room temperature and higher, we find that for atoms which have atomic weight greater than 40, specific heat is generally found to be around 3 R. But for the low temperature range, its failure is in the low temperature range. The specific heat of all elemental solid, it approaches 0 as T cube for insulators as T in metals. In superconductors, this drop is even faster. Second failure is in case of the magnetic solids, there is a large contribution to the specific heat near the temperature at which the magnetic moments become ordered. If the low atomic number cases and high melting point elements, this show a lower specific heat than that predicted by Dulong-Petit's law. Then again, in case of electropositive metals also, specific heat, it increases much above the 3R value. So, if I plotted the solid line at CV equal to 3R constant value for different temperature, according to Dulong-Petit's law, that should be the value. However, actual prediction is somewhere around what is shown by the dotted line. It does not remain constant at low temperatures, rather it falls to 0 and the fall is as shown in this, as shown by the dotted line. So, to solve it, Einstein tried to resolve this specific heat problem. He tried to resolve it by applying Planck's quantum theory, and his assumption was a crystalline solid is made up of capital N number of atoms per mole, and that could be regarded as an array of atomic oscillators which are vibrating in 3 independent directions with a constant frequency nu. Now, if these are vibrating, if these are Planck's oscillators, then if they are vibrating with a frequency nu, then the energy of these oscillators, as we know, will be an integral multiples of h nu. They cannot have any arbitrary values, rather they will have energy in integral multiples of h nu. Einstein regarded all these atoms as independent of each other and each of them are vibrating with a frequency nu. So, their energy states will be an integral multiple of h nu. Then they will interact according to Hooke's law. So, there are 3n independent number of oscillators. There are 3n modes of independent modes. So, there should be 3n independent oscillators, and the total energy of the crystal will be sum of the mean energies of the individual oscillators. Each of the 3n harmonic oscillator will have quantized energy, and let's represent that by epsilon n, that should be equal to n h bar omega, or that should be equal to n h omega, n h nu, omega is 2 pi nu, okay, where the quantum number, now n can have values 0, 1, 2, 3, 4 etc., and omega is 2 pi nu. The number of oscillators Nn in each of the energy state will be determined by the Boltzmann function. So, Nn will be equal to n naught e to the power of minus epsilon n by kT, or that can be equal to, that will be equal to n naught e to the power of minus nh nu by kT. N naught is the number of oscillators in the 0 energy state. Then the average vibrational energy of the oscillator epsilon bar will be given by epsilon by n, which will be summation over n, nn epsilon n upon summation over n, nn. That should be equal to h nu upon e to the power of h nu by kT minus 1. This I label as my equation number 6. Taking into account 3 independent harmonic oscillator, then total internal energy will be given by, per mole will be given by E mole will be 3 nh nu upon e to the power of h nu by kT minus 1. So, specific heat, which is equal to dE by dt at a constant volume, will be equal to 3 nk into h nu by kT whole square e to the power of h nu by kT upon e to the power of h nu by kT minus 1 whole square. So, Einstein's specific heat curve, that is fairly close to the experimental curve except at the low temperatures. In this case, this is the Einstein specific heat curve. The solid line Cv equal to 3R is the Dulong-Petit's law, the classical value. The solid line is the Einstein specific heat curve. the dots are the experimental points. What we find is Einstein's specific heat curve is fairly close to the experimental curve except at low temperatures. If I go to the low temperature, there is a deviation from the actual experimental values. Then in this region, the Einstein's specific heat approaches 0 much more rapidly than that is observed in the experimental values. At high temperature, it approaches the classical value. So let us study it in the high temperature range and the low temperature range, how Einstein's specific heat formula, that is the CV, which is my equation number 8, it behaves. Then let x be equal to h nu by kT. At high temperature range, h nu is very much less than kT. So my equation number 6 becomes equal to epsilon bar becomes equal to h nu upon e to the power of x minus 1, or e to the power of x. Now I can make an expansion 1 plus x square by 2 factorial plus x cube by 3 factorial and so on and so forth, which I can write as 1 plus x, neglecting the higher order terms. So at high temperature, I can write epsilon bar as h nu by x, which is equal to kT. So E mole will be equal to 3n epsilon bar, which is equal to 3n kT. CV will be equal to dE by dt at a constant volume. That means that will again be equal to 3nk, which is equal to 3R. 3R is the classical result. That means at high temperature, Einstein's specific heat equation, it approaches the classical result, which is what is observed experimentally also. Low temperature range. Now let us study this curve at the low temperature range. In the low temperature range, h nu is very much greater than kT. So e to the power x will be very much greater than kT. So epsilon bar will have the form h nu upon e to the power of h nu by kT. So E mole will be equal to 3n epsilon bar, or this I can write it as 3n h nu e to the power of h nu by kT. Specific heat will be dE by dt at constant volume. So that will be equal to 3nk h nu by kT whole square into e to the power of minus h nu by kT. This indicates that the exponential term, now if I look at this equation number 9, that is CV becomes equal to 3nk h nu by kT whole square into e to the power of minus h nu by kT. This shows that the exponential term is more important than the term h nu by kT whole square in determining the variation of CV with temperature. CV is the specific heat with temperature. With the decreasing temperature, the specific heat, it drops exponential. So according to Einstein's model, with the decrease in temperature, the specific heat should drop exponentially. The drawback of this model is that it could not explain the variation of specific heat with temperature in the low temperature range. So as a solution, Debye gave a model. Debye pointed out, next came Debye's model. He gave a model and he pointed out that the source of error in the assumption, error lies in the assumption that all the atomic oscillators, they are vibrating at a constant frequency. That was the problem that Einstein made in his assumption that all the atomic oscillators, they are vibrating independently and at a constant frequency. This is not, Debye said that this is not justifiable, since all the atoms, they are elastically coupled to their neighbors. All the atoms, they are elastically coupled to their neighbors. So the atomic oscillators, they cannot be taken as independent oscillator. Debye considered the situation that solid is vibrating continuously as a continuum, elastic continuum. The solid is continuously vibrating medium and it is acting as an elastic continuum. This gives rise to a spectrum of frequencies instead of a single frequency. In Einstein's model, the assumption was all are vibrating independently at a constant frequency. Debye gave the suggestion that instead of a single frequency, a range of frequencies are excited. Once the frequency distribution curve is known, we can calculate the total internal energy and hence the specific heat of the solids. Einstein's model, that is given by frequency should be a constant nu e. Debye suggested that instead of a single frequency, a range of frequencies as shown in this figure will be excited up to a frequency which he labeled as the Debye frequency nu d. Now, internal energy of the Debye solid should be equal to integral over all the allowed frequencies epsilon bar nu into G nu d nu. Now, G nu d nu, it represents the number of modes whose frequencies lie between the interval nu and nu plus d nu. Using my equation number 6, and G nu d nu will be given by 4 pi v 1 by V L cube plus 2 by V T cube into nu square d nu. V is the volume of the solid. So, E will be given by 4 pi v 1 by V L cube plus 2 by V T cube into integral limit 0 to nu d h nu square d nu upon e to the power of h nu by k t minus 1 h v nu square. In terms of this equation, nu d cube equal to 9n upon 4 pi v 1 by V L cube plus 2 by V T cube whole to the power of minus 1. This equation number 12 will take the form of E will be equal to 9n by nu d cube 0 to nu d integral limit 0 to nu d h nu square d nu upon e to the power of h nu by k t minus 1. If I simplify then and take x to be equal to h nu by k t and d nu will be equal to k t dx upon h and x d, let that be equal to h nu d upon k t, then this equation will take the form E will be equal to 9n k t by h nu d whole cube into k t integral limit 0 to x d x cube dx upon e to the power of x minus 1. Now, we define a temperature. Debye defined a temperature theta d according to the equation h nu d should be equal to k theta d. So, theta d becomes equal to h nu d by k, or x will become equal to theta d by t. So, this equation number 15 takes the form E should be equal to 9 n k t t by theta d whole cube integral limit 0 to x d x cube upon e to the power x minus 1 dx. So, this shows that energy of the total system, it does not depend explicitly on the volume. This equation shows that energy according to Debye model, the energy of the system, it does not depend on the volume. Now, let us again consider for the high temperature range, the low temperature range and the intermediate range. How this equation, Debye equation will vary. In the high temperature range, x is h nu by k t. In this temperature, T is very much greater than theta d. So, k t will be very much greater than h nu. So, even when nu equal to nu d, x will be small. So, in this equation, the integral will be, I can take it as 0 to x d x cube e to the power of x minus 1 dx, that becomes equal to integral limit 0 to x d x cube by x dx, which is equal to x cube x d cube. If I integrate and put the limits, that will take the form x d cube by 3, which becomes equal to 1/3 of theta d by t whole cube. That means E takes the form of, so if I substitute it back, that becomes equal to, in this my equation number 16, then E will take the form of 9 kT into 1 by 3, which is equal to 3 nkt, which is again my classical result. This means that in the high temperature range, the specific heat is same as that measured by the Dulong-Petit's experiment. That means T will be, when T becomes very much greater than theta d, then every mode of oscillation is completely excited and the average energy is equal to the classical value of kT. So, this behaves as the classical, that means it approaches the classical value, the specific heat value, it will approach the classical value. Cv will become equal to 3 Nk. Let us see what happens in the low temperature range. In the low temperature range, T will be very much less than theta d. So, kT will be very much less than h nu d. This means I can replace the upper limit of the integral by infinity. So, the integral takes the form of pi to the power 4 by 15. Substituting, we get E becomes equal to 3 by 5 pi to the power 4 nkt T by theta d whole cube, or Cv becomes equal to 12 by 5 pi to the power 4 3 nk T by theta d whole cube. This, that means Cv, it varies as T cube. This is the famous Debye T cube law for specific heat at low temperature. This shows that specific heat, it will fall as T cube. And if I see the graph for the dotted line, Cv equal to 3R is the classical result, the other one is the Einstein result. The experimental points are shown by dots and the Debye value is shown by the solid line. We find that there is a good approximation. It explains the low temperature variation of the specific heat with temperature very well. Okay. This, the T cube dependence can be understood from the form that only at low frequencies, only those frequencies which have energies greater than h, having energy h nu less than kT are excited and they are propagating. So, this case, the number of modes are found to be nu cube will be proportional to T cube. Only these at low temperature range, the increase in energy will be, the rise in temperature at low temperature range causes new higher frequencies to be excited. So, that will be varying as T cube. In the low temperature range, there are two methods by which the solid, the rise in temperature can occur. It can either increase the average energy of every normal mode, or it can excite the newer number of normal modes can be excited. That will be proportional to T cube. The second case, the first case will be proportional to T. So, the total energy will be proportional to T to the power 4. The variation, as I said, average energy of the oscillator, that is proportional to T. The increase in the normal modes, that will be proportional to T cube. So, the total will be proportional to T to the power 4. Hence, the specific heat, this is the energy excitation, specific heat, first derivative of E at a constant volume. So, that will be T cube variation. It is in the intermediate temperature range that the Debye model fails. It is in the, for T less than theta d by 50 or T greater than 0.2 theta d. This Debye model explains the specific heat variation nicely. However, it is only in the intermediate temperature range that this Debye model fails. In the very high temperature range, even the classical result of Dulong-Petit's law also agrees, but in the intermediate range, which is shown by the dotted line, it is what it fails. This is all about the specific heat for today. Thank you.